Let's go for another type of testing, soil in situ. We are still on chapter number 2. Okay. This time we are going for the pressuremeter test, which is 7 point this chapter. Okay. What is it about? How to conduct the pressuremeter test, how to use the test result to obtain soil parameters. These are the points we are going to discuss in this video. Okay, so this pressuremeter test, this is the designation, American Society for Testing and Material. Okay, PMT, pressuremeter test. Just when you hear pressure, in pressuremeter you hear pressure, right? So it's just about applying uniform pressure to cylindrical cavity in the ground. So you make a hole, cylindrical shape hole, and you apply the pressure in the hole uniformly, and you monitor the pressure and the volume change. Okay, so this is the equipment used. So you have this bottle, sometimes gas. Okay, and this is the pressure meter actually. This probe is pressure meter. So you will measure both pressure and the volume change. We will see how it works soon. So this test helps to assess the soil compressibility. You know if the soil is too much compressible or not compressible. And it will help to assess the estimate the ultimate pressure the soil can support before failure. Okay, due to lateral pressure. Because if you make the hole in the ground and you apply pressure, okay, lateral pressure. What is the maximum pressure, lateral pressure the soil can support? Okay, so in this test, the main task is to monitor relationship, as I said, between pressure and soil deformation. And by soil deformation, we mean that the volume, we can obtain that from the volume of the probe. Okay, volume change, because the volume will increase and push the soil back. So this involves drilling hole. You make a hole, okay, mean pre-drilling, and the diameter of the hole is between 1.03 to 1.2 times the nominal diameter of the probe. Okay, you see this probe diameter. Of course, there are several sizes. We will see this also now. So the diameter of the probe is considered when you make the hole. So you make the borehole having 1.03 to 1.2 times the nominal diameter of the probe. Okay, and you insert the probe at the desired depths where you want to test to know the strength of the soil before you conduct the test. Okay, so as I was saying, there are many probes, different sizes. Okay, the probe is inserted into the cavity and inflated to expand. Okay, you inflate the probe to expand. There are several types, and here are some photos of some probe. This one here is like self-boring, means the probe is going down itself, boring and going inside itself. Okay, self-boring probe. So here is illustration how it works. The borehole is like this. Sometimes you need casing because some soil cannot, you cannot dig a hole too deep without the soil collapsing inside it. So you need some time to sustain, support this. But of course, you cannot put anything where you want to perform the test, okay? Yeah. That will be the direct contact between the probe and the soil. So here, this part and this one are these guard cells, okay? And this middle one is the measuring cell. This part is the measuring cell, okay? This is how it works. So these guard cell are just used to control the ending conditions, okay? The size, diameter of probe that is most common one is 58 millimeter, means 5.8 centimeter as a diameter, and the length is 42 centimeters, okay? So we can use both liquid or gas to expand the probe. And the guard cell, these ones, the guard cells, okay, here and here, this one and this one, as I was saying, are expanded to reduce the end condition effect in the measuring cell, which has the volume of about, please remember this because we will use this in example soon, 535 cubic centimeter. This is the volume, about the volume, the initial volume of the probe, okay? And then, because you need the initial volume to know its volume change, okay? Because as we explained previously, this is about monitoring the volume change and pressure applied and the volume change going with it. So you need to know the initial volume before you be able to understand what is the amount of change in the volume, okay? So these are some diameters, probe diameter, okay? And the borehole diameter also, nominal one and maximum, okay? Examples. So if you are going to perform the test or if you are leading, you can choose this depending on the diameter of the probe you are using. Please refer to this table and select. This is recommended by the American Society for Testing and Material, okay? So to conduct the test, how does it work exactly? So as I explained, we have measuring cell and it has volume about 535 cubic centimeter. Let me see. Yeah, this one. Okay, this is the initial volume. Okay, so let's go back. Here is the test, how it is conducted. So you measure the measuring cell volume, the 555 cubic centimeter. That's one example. It's not always the case. Okay, but you measure that and you insert the probe in the hole, the boring hole. Okay, like this. You see, at the initially this hole was like this diameter here. Okay, like this, as you can see. You insert the probe. This is same equipment, right? Yeah, and here is, you can see green line and red line here. These are mainly like probably the volume change and the pressure applied. Okay, volume and pressure applied. So The pressure is applied then, okay, after inserting the probe. The pressure is applied in increment. You increase step by step, little by little. And for each increment of pressure, you measure the new volume. Okay, don't forget that you have the initial volume here, which is the volume of the probe. And for each increment of pressure applied, you measure a new volume. Okay, sorry. So the process is continued until the soil fails. Until the soil fails, okay, or until you reach the maximum limit of the pressure you can apply. Okay, because some soil are too hard that the pressure, the available pressure is not enough to make them reach failure. Okay, so the pressure limit of the device can be reached before failure of certain soils. In that case, just you have to notice at which volume this pressure limit is reached. Okay, so the soil is considered, this is just like it is assumed that the soil has failed when the total volume of expanded cavity is about twice the volume of original cavity. Okay, and if you see the original cavity, the volume is like this. So if you have twice this volume, you can consider that the soil has failed because there is no visible like phenomena that will show you directly that okay, the failure has happened. So here is how it works. So after that, after completing the test for at this place, for example, you make the probe come back to the original shape. Okay, so it means you deflat it and you advance for testing at another depth. So some self-boring probe will just make the boring at the same time and go deeper. Okay, and you do another test so that you can have continuous, yes, continuous measurement for each depth you measure. Okay, this is just example of like some people may doing the test. So, but in this case, this is the probe just waiting to be used. Okay, and here is they just want to like drilling borehole here, drilling a borehole for with the method wet rotary. I think we have seen this method before. I'll explain this method before. Okay, and the pressuremeter control is here, and now they are getting ready to insert the pressuremeter into the borehole. Okay, just the measuring equipment. You can see this here, connection here, this cable connecting. Okay, same here, connecting the rods. So the result of this pressure meter are expressed as I was saying in the form of pressure versus volume. Okay, so the recorded volume change is related to the pressure, applied pressure, something like this. So this is just illustration, the curve illustration. You have different zones. The initial volume is here. This one is the initial volume plus V0, something like that. Okay, corresponding to this P0, the pressure corresponding. Okay, and this one is here, what is we call V0, this initial one, because this one is not zero. Okay, V0 plus VM. The VM, it bring you to the middle of this. Okay, and we have V0 plus VF final. Now twice V0 plus V0 means this one, twice this volume here. Okay, that is the failure or the maximum pressure limit pressure. Okay, so if you check this curve, you have 3 zones, and we are going to describe them soon enough. First one, zone 1, from here to here, zone number 2. Okay, and here to here, zone number 3. Here is an example of this. This is a result for an actual test. Okay, actual test. Result of actual test. Okay, do you understand this? This one, as you can see, the pressure is here at the horizontal axis, and the volume is here, vertical axis. But this one is like opposite. The pressure is vertical here, and the volume is here. So if you want to understand this one, the result in this, maybe you have to flip this one. If you take this one, this corner of the figure, and flip it, put it here, then you will be a graph that is comparable to this one, this shape. Okay, it is like we can consider this shape. Okay, this shape. But anyway, maybe loading, first loading, okay, unloading, and loading again, unloading. Okay, you can continue this. So we will have a deeper discussion about this result before the end of this video. Okay, so let's continue. I'll put this figure here since we are going to describe it. So this first zone, this one, okay, this first zone represents the reloading portion, during which the soil around the borehole is pushed back at its initial state. Because when you make boring, sometimes soil will collapse in the hole, in the borehole, right? Soil will collapse. So if you push, you start pushing, initially, the soil will go back to initial state, like how it was in the ground before even drilling. Okay, because after drilling the hole, the soil will like get loose and try to collapse in the hole. But if you put the prop and try pressure, pushing back the soil for each side, at first the soil will get back at its original state, initial state, before even you disturb it. Okay, that is this portion here. Now you have reached the limit of the original state of the soil. At that pressure P0, you will see that we can use this pressure to obtain something. Okay, so the pressure here is the in situ total horizontal stress. This is what I was saying, in situ total horizontal stress. Okay, it means sigma H. You know sigma V, right? So you should know sigma H. Okay, Sigma V is vertical total stress. Sigma V is horizontal total stress. Okay, they are not same. They are related. There is a relation between them, like K naught, but they are not same. The second zone, this zone number 2. This zone represents the, let's say, slow elastic zone. In this zone, the volume versus cell pressure is almost linear, practically linear, as you can see. It's linear zone. Okay, and this zone is very important for us. So this zone, the pressure represents the creep or yield pressure. So this zone is the zone where the soil is still trying to resist. Okay, after the yielding, from here the soil has yield. Okay, yielding creep or yielding pressure. The third zone is this zone is like plastic zone. Okay, and the pressure represents the limit pressure. You can see here limit pressure, and you will see that in many formula this limit pressure is used. So here I want you first to notice delta P and delta V. You see delta P, okay? This pressure PF minus PO, okay? Delta V is the volume corresponding to the PF minus the volume corresponding to the P0, PO. So with the formation property, the test allow to get both the formation property and coefficient of lateral earth pressure. Okay, modeling the shear failure based on the Coulomb friction failure theory. Okay, the pressuremeter modulus. Okay, pressuremeter modulus, which is related to elastic modulus, you will see, of the soil is determined with the use of theory of expansion of an infinite thick cylinder. Okay, so deformation property are derived from pressuremeter modulus, which can be related to the elastic modulus. So this equation, okay, as I was saying, this delta P here and delta V here, because we need them to obtain the elastic modulus. Okay, so VM, actually VM is just the volume here in the middle. Can you confirm that the volume here is what we are calling VM, because it is like V0 plus VM. Okay, the initial volume plus VM. Okay, it is this one. So the formula is here. VF, the volume here, F plus V0. Please, this is it V or mu? Not mu. But you can see the difference, right? This is capital V, this is small v. So delta P, already explained. Delta V, already explained also. And the Poisson ratio, mu, this is sometime around 0.33. This is common value for soil, for sandy soil mainly. Okay. The limit pressure, this one, as I explained, sometimes the soil collapses before reaching the limit pressure. Sometimes the limit pressure is reached before the soil collapse. That's why this limit pressure is usually obtained by extrapolation and not by direct measurement. You just extrapolate and you guess it will be about around here. By calculation, calculate using extrapolation, okay? So as I was saying, in order to overcome like difficulty related to preparing the borehole, okay, to the size needed, because as you see, you have seen at the beginning of this video, the American Society for Testing in Material is recommending some sizes related. The size of borehole is related to the size of probe. Okay, so this is sometimes difficult to respect. That's why now we have self-boring pressure meter. Okay, that is being developed. Okay, here is how it works. You see the measuring cell here, right? So this, the head is self-boring. You can see the head here, and you progress automatically after finishing the measurement. You just do self-boring and you progress by yourself. You don't need to remove or to make a mistake in the size dimension of boring hole. You can get more information about this from this reference, okay? Correlation. We have several correlation between the soil parameters and this result. This first reference is suggesting this equation to obtain the pre-consolidation pressure based on the pressure limit, okay? So the pre-consolidation pressure 0.45 times is 0.45 times this limit pressure, okay? Another reference is proposing us this as the underlying shear strength of clay, okay? If you have the pressure limit, the P0 means the initial, the state pressure, and NP can be obtained from this relation, okay? The problem is NP include also CU and then shear strength. So some value of NP are given here between 5 and 12, and the average being 8.5. So you can take this average and calculate the underlying shear strength, okay, for your clay. These references related try to obtain relation between the field standard penetration test number, the standard penetration test we discussed before, and the modulus, Pressuremeter modulus. Okay, so the Pressuremeter modulus for clay can be obtained from this formula using N60, means the N value. Okay, in sand, use this equation, this formula. So the shear strength of soil roughly can be obtained from lateral pressure, pH, lateral pressure, when the pressure meter membrane fully contact the surrounding soil. Okay, at this point, the lateral pressure at rest can be approximated used the following expression, this one, okay? Because as we said, this is just using the P0, okay? If you replace the initial contact when the soil return to its initial position, the pressure you have at that time is equivalent to the lateral pressure to the initial condition the soil was in the ground in situ. So you can obtain the total horizontal stress, okay, from that, or total effective horizontal stress. And I did explain what is K naught, K0, okay, the ratio between horizontal effective stress and the vertical one. So in this case, this one is exactly the pH here is, I will go back a little bit again. This figure is what I want. Is equivalent to this P0. Do you remember when we explained this portion, this first zone, is the zone where the soil returned to its original position, original state, okay, before disturbing the soil. So this P0 is what is here as pH. This P0 is exactly the horizontal effective stress. Vertical effective stress is here, right? Okay. So if you have this P0 or again pH, you can obtain the K naught here. Alternatively, there is also another way. Instead of expressing the result by pressure versus volume, we just do pressure versus radius of the pressure meter, because the volume is related to radius of the pressure meter. Pressure meter radius will increase when the volume is increasing. This is an example of this kind of test. You can see here pressure, and here is the radial displacement, okay? So it goes like this: loading, unloading, loading again, unloading, loading, so on. Loading, unloading. Yeah. So, and unloading completely. Okay. So some references worked on this kind of relationship and obtained some useful relationship, especially when the pressure meter test is conducted in sandy soil. Okay. They obtained this pressure meter inflation pressure at elastic limit, which is PE, elastic limit. Okay, we have explained what is elastic limit here. So this one is here, PE, this pressure. pH is also like P0, as I explained. Multiply 1 plus sinus of phi. Phi is the internal frictional angle. So from this, we can obtain this angle from this relationship. In the range of plastic deformation, the gradient of log of radial deflection, this one, versus log of inflation pressure is given by this one. This modulus. We will see soon how we can use these two to obtain soil parameters. So in this mu, this V is dilation angle related to the slope of the volumetric strain versus shear strain, like this. Volumetric strain, shear strain. This angle here. This is just illustration. We have talked about this before also. So we are going to do one example on how to use the result of this test. Here is the result. We will discuss this result to see how we can use this result of this test. Okay. So as I said, you should be careful about here is pressure and here is volume. Not same as here, volume and pressure. Okay. So this one result is at 10-meter depths. The result here. Okay, this is one information. And the plot here, we can see that we have up to 120 here first, without reaching the limit. Do this 120 without reaching the limit. Then unload and reload again until the limit now, which is 150, around 150 here. Okay. We can also see that the final unloading, this is the final unloading, this one is like parallel to this initial loading and unloading. These two are parallel. You know? So from this initial loading, unloading, reloading portion, this portion, we can say that we can see it here. This corresponds to this portion, this one. Okay. So it means the linear portion start from this to here, right? So in this case, this is like curved. It's curved like this way. Okay. And the linear portion start around here until here. You can say that a linear portion. So from this point, this point is around, maybe it is here, okay? Because this one is unloading. Loading, reloading is here, okay? This line. So the reloading is this one, okay? So we should focus on here. The linear portion is this one. So from here to here, it corresponds to this. 20 to 35. See, here is 40, 20 here. Okay, let's say 45, 20. This is the beginning of the linear portion. And the end is around here, 140. Okay, so the rest from here to here, from here to this part, is this portion of the curve correspond. I know it's a little bit difficult to understand since they are not the same orientation. But yeah, the portion the linear portion is from 20 to 100. And the first portion from 0 to 20. The linear second zone from 20 to 100. And the third zone from 100 to this one, to 150. 150 being the limit. So do you remember this? So as I said, the P0 is similar to pH here, which means the soil has returned to its initial position, initial state. Okay. So based on this, we can estimate the elastic deformation of shear strength parameter. First, this 20 here correspond, as I said, to the pressure 20. Okay, if you want it in kilopascal, please multiply by 6.9. Okay, this one is imperial unit, not international system. Okay, the international system, if you need it, multiply here by 6.9. But this one is hopeful fortunately in cubic centimeters. So 20, okay, this 20 here correspond to this P0 or again pH. Okay, so from that, we can say that the in situ lateral soil pressure at rest is 20. Okay, so if we assume that there is no groundwater at this depth, so we can calculate. Do you remember the depth is 10 meter, about 30 feet? Okay, so we can calculate the vertical effective stress by using just the depth and the unit weight. So we are trying to calculate this. Okay, by doing that, we can obtain this. And dividing, we can obtain this K naught, by dividing this one by what we got here. Okay, and we can obtain it. The unit is not kilopascal here. In kilopascal, this one is maybe in kilopascal. Okay, the one in brackets. Anyway, you can obtain the K naught here, which is the ratio between sigma H and sigma V. Next, I will put back this here. We will try to estimate this one, the modulus, pressure meter modulus. So from this, before going there, from this K naught, we can try to obtain the frictional angle. If we assume that this formula is correct, which is very common formula to obtain K naught, 1 minus sinus of the frictional angle. So from this, since we know the K naught, we can obtain this one just by using this relationship. It is about 11 degrees. Okay. Now we are trying to obtain this elastic modulus. First, we go for VM. VM, you see the formula for VM, right? So VM is obtained from this point and this point. Okay. The equation is here. V0 plus VF divided by 2. So our V0, this one, not same as this one, okay? The first one we measured is 20, and the last one is, sorry, not 20, corresponding to 20, 35, okay? 35, and this one is 45. Remember, 100 correspond to 45 here, okay? Between this point and this point and this point. So the volume here, 45, plus this one, 35, divided by 2, okay? Divided by 2. And minus 20, okay? Do you know why we did minus 20? Because 20 is the initial volume here. This V0 here. As you can see, the initial 20. This V0. If you want, you can take this one, okay? The volume here is V0 plus VF. V0 plus VF, okay? Right? So, this V0 plus VF, in our case, it corresponds to 45. This one, volume here. And this one, this point is V0 plus this small V0. These two, okay, correspond in our case to 35, the volume corresponding to here 20. Okay, so if you do this one plus this one, you will see that you will obtain V0, this V0 plus VF plus twice this capital V0. And if you divide it by 2, you will obtain V0 plus VF divided by 2 plus 1 time this capital letter V0. So you have to do minus that same, okay? Please do that. You will see what I'm saying. It's very easy. I didn't do the mistake. Make this one V0, capital V0 plus VF plus capital V0 plus the small V0 and divide by 2. This is the formula here, okay? You will see that you will obtain exactly this plus this capital V0. Then by doing minus this 20, which is the initial here, 20 volume, the initial volume, you will obtain then exactly, you will obtain exactly this. Okay. Now, anyway, let's try now to obtain this part. Okay. This part divided by this part. So that one should be easy, I think. Okay. 100 minus 20, 100 is here. 120 is here. Okay. That is the pressure. And we divide by the volume. It is 45 minus 35. Okay. So the volume corresponding to 100 is 45. Volume corresponding to 20 is 35. So as you can see, everything will depend on how good you are at identifying the linear zone. Okay, that zone is important. So after doing many conversion, you can obtain this like this in kilonewton per meter power 5, something like that. It's big. I will put the result here. Okay, this VM we obtain here in this one. So if we have this delta P divided by delta V, and we have VM, and we know this one already, it's 20, and this one we will consider it 0.33, then we can obtain this easily, right? We can obtain. So the result, we will consider this. The initial volume is, in our case, the V0. This V0 is the volume for, how to say, for the probe, 535. Okay. So the elastic modulus for lateral deformation is about this. Okay. We calculate this by just using this equation. The initial volume of the probe is this one. This is the volume of the probe, okay? Not related to the initial volume here. Related, but not same as this volume here, okay? This is maybe a little bit confusing, I think. So please remember, in this formula, this is the volume you are supposed to use. This one. Another example, we are going now to use this tool. This one is now using pressure versus the radius of the probe, increment in the radius, not the volume anymore. So this table we have here we have here collected pressure and expanded radius like this. So we can make the figure like this. By using this data, we can obtain this. Okay. We can do this. So in this figure, the pH, okay, horizontal one is about this 1.5. This limit, because pH, the limit of this zone 1.5 about this. Maybe the linear portion is around here, and this is the last portion. So 2.5 here, PA, which is similar to, let me see, similar like to this one. Okay, these are from different books, so I didn't work on the uniformity to make it uniform yet. So if we apply this equation, we can obtain this one. By applying this equation, we can obtain this. This is just the slope, okay? And then from that, we can obtain this phi, about 42 degrees. Now, let's use this one, okay? Let's use this. The slope is around, okay, 3.1. The slope, the gradient of log radius to log t with plastic range. We can obtain this. Then by applying this formula, this equation, we can do something like that, and then we can obtain this angle. The dilation angle can be obtained. Okay, it is about 11.5. Okay, then if we have this frictional angle for the 42 and dilation angle is 11.5, then we can obtain this residual frictional angle. Okay, residual frictional angle will be found to be about 33 degrees. Okay, that's all I think. So thank you very much for your time, and see you next time.